There we go. Okay. So guys, you probably noticed that I didn't pick up your chapter 19 outlines yet. That wasn't by mistake. And I pray that none of you are scrambling right now to finish them because they should be done. But what I would like you to do is grab them, please. I wanted you to have those as a reference as we start into chapter 19. And guys, I just want to lay the question at your feet as we get started today. So you may even want to open up your book to chapter 19 so that you have it as a reference. So, guys, having looked over chapter 19, do you understand now why I didn't have you do 19 when you were doing 5? It creates so much confusion. You've got H's, you've got S's, you've got G's, you've got entropy. It kind of sounds like enthalpy. You got all this stuff going on, and it really can just get confusing. But now that you sort of have a grasp of chapter 5 and heat and enthalpy, we can now bring the concepts from chapter 19 into play. So guys, my question I have for you is this. What are the big ideas in chapter 19? What's the important stuff? What are the tricky bits? What are the things that you wrote down under questions because you didn't understand them? Because those are probably the important pieces. So free energy. And let's just make a laundry list and then we'll talk with them in a little bit greater depth as we go. So guys, free energy is big. Yeah? Okay, so let's address that really quickly. Guys, when we talk about vibration, rotational, translational, all of those things, that is actually not something we're going to do a deep dive on as a class. It is mentioned in the book relative to entropy. And so in the context of entropy, you need to understand that one of the, and guys, you understand entropy is disorder, right? One of the things that gives substances or systems disorder is when they wiggle. And there are different ways you can wiggle, but we're not going to really do a deep dive on wiggle. What else? Okay, so guys, this is going to blow your mind. Reversible, irreversible, and spontaneous. These are critical concepts. And it's actually one of our goals for today is what is a reversible process? What is an irreversible process? And what does that have to do with something called spontaneity? What else? Yeah. What is what? What are the criteria for spontaneity? Irreversibility. We'll talk more about it. So that's where we're, yeah. So what is it that makes a process well, first of all, what does it mean? But then, guys, what has to be true for a process to be spontaneous? That's a big question we need to resolve. What else? Other things that jumped out at you in chapter 19? Yeah, so many equations. Thankfully, our equation sheet is the distillation of the important ones. Go ahead, Caleb. Oh my gosh, yeah, and actually this is one we are going to talk about, and it's lovely. You're going to like microstates. It's pretty good. We're not going to get to it till Thursday. Wait, no, Friday. Because remember, guys, we said Wednesday we're going to rewrite tests. We probably won't get to microstates until Friday, but it's really cool. I like it. What else, y'all? Second and third laws of thermodynamics. Guys, let me make a suggestion to you right now. Don't Google them, okay? If you Google second and third law of thermo, your head's going to go, it's crazy. Okay, go ahead and try it. But what you're going to find out, guys, is that the second and third law of thermodynamics are such big concepts that if you Google, especially the third law of thermo, if you Google that, you're going to find 15 different definitions of it, depending on who it is that's writing it, and all of them are right, they're all correct, but none of them sound the same. So guys, I would encourage you, well, certainly you have to know the definition we need to know for AP. You're welcome to do deeper research into this on your own, but understand there is the possibility your brain's going to explode. So what else? Other things that jumped out? Okay. So guys, let me do this with you then. Let me give you the big picture, and I would encourage you to put this in your notes. So guys, this is the big deal for chapter 19 and for chapter 5. As this all comes together, here's the big question, here's the big point, here's the way the AP gods are going to, no pun intended, hold your hand to this fire. Okay? Here's what they're going to do to you. They are going to, through all sorts of crazy avenues, get you to this one important question. Is this process spontaneous? That's it. That is the big question in this unit. Is this process spontaneous? And then whether the answer is yes or no, at what conditions is it spontaneous? So again, guys, the big question is it spontaneous and why? So again, guys, the two big questions, is a process spontaneous and why? Now, here's the thing that's interesting. You know, Vanessa said a minute ago, oh my gosh, there's a bunch of equations, right? Chapter 19 was very equation rich. The thing that's interesting in chapter 19 is that the majority of the questions that we've seen on chapter 19 on AP tests have been qualitative in nature. They've been non-mathematical. And so they love to dig at the concepts in chapter 19. Doesn't mean they can't ask you to do a little bit of math, but typically chapter 19 questions tend to be qualitative in nature. Okay, are y'all caught up with me in your notes? All right, so guys, this is the way the thinking then goes, and this is how we're going to tie this all together. Are you ready? It goes like this. The big question is a reaction spontaneous? So in order for a reaction to be spontaneous, what has to be true? It has to be irreversible. Now, what is it that makes a reaction irreversible? It gives off energy. You tracking with me? So, is it spontaneous? Has to be irreversible. If it's irreversible, what does it do? It gives off energy. Now, guys, this is the place where our path is going to separate. So, follow me. So, now we're talking about energy, right? So, let's go back to chapter 5. What do we know about energy? How do reactions lose energy? Work and heat, but we're not going to do work, so that's then heat. But guys, here's the problem. In chapter 19, we find out that there's a whole other kind of energy that isn't enthalpy, it's entropy. So the way that this is then going to work is this. Is a reaction spontaneous? That's how we're going to wrap up the unit next week. In order to understand if it's spontaneous, we need to know if it's irreversible. We're going to talk about that today. But in order for a reaction to be irreversible, it has to give off energy, right? And we understand that giving off energy can happen through an enthalpy change, but you're going to find out today it can also be an entropy change. So we're going to bring entropy into the conversation. Then we're going to connect that to reversibility, and then we're going to connect that to spontaneity. You get the idea? That's the big idea for chapter 19. Now guys, one last thing we need to talk about, and then we're going to get into the details. So we understand there's enthalpy, we understand there's entropy. Guys, where do enthalpy and entropy come together? Gibbs free energy. Okay? So that's the connection. Reactions can give away heat, and they can change disorder, and those come together in what is called Gibbs free energy. So that's the summary of the unit. So guys, let's kind of get this in concrete form so that we're all okay. So it goes like this. Guys, what are the most important concepts in chapter 19? First of all, spontaneous processes. That's the big deal. Now guys, please understand this is an overview. This is not intended to take the place of learning. We're laying out the roadmap so that you know where we're going. So guys, what is a spontaneous process? We're going to lend some definitions to these. So guys, a spontaneous process is a reaction that takes place on its own without any outside intervention. Does that kind of jive with your understanding of the word spontaneous? Like my wife would tell you that when we were dating, I was much more spontaneous, and now all I do is ride my bike. So, you know, there's that time when you're dating and you're always just looking for ways to woo this woman that you hope someday will marry you. And she doesn't have to prod you, right? She doesn't have to come to you and go, hey, you really should take me out, because you just do that spontaneously, meaning there doesn't have to be any outside intervention. You're doing this stuff on your own without her having to poke you to do it. Now she has to poke me to get me off my bike. But the idea is if you're spontaneous, you're doing things without somebody needing to say, hey, go do this. You get the idea? That's fun. Can I give you, by the way, my dating advice? This is the one bit. Okay, I'll give it to you once. Here's the deal, guys. When you get out of high school, although some of you think you may actually be dating right now the woman you think you're going to marry, but here's the deal. When you find, and this is for guys, when you find the one, okay, and you've decided this is the one I'm going to marry, guys, when you're dating, go as low as you possibly can without losing her, okay? Seriously, like start at McDonald's and maybe work up to Wendy's. But seriously, you don't want to go tree room at Sundance, because if you go big, then once you're married, you got nowhere to go, and you'll always look like an idiot because your wife will always be saying, why don't we do things like we did when we were dating? You understand what I'm saying? So guys, but it's a fine line, because you don't want to go so low that she's like, this guy's not interested, and she walks out. So it's got to be enough to keep her around, but not so much that you got nowhere to go but down once you're married. Got the idea? All right. Now here's the problem, and this is for the ladies. Ladies, when you meet that guy and he's going super big, understand that when you get married, he's got nowhere to go. So if he can maintain super big, give him credit. Okay? Seriously, he's trying. There's nowhere, my wife, anyway, all right, I give up. I digress. It's all, my wife, never mind. All right. I know. This is recording. I'll share it with my wife. Okay. So guys, you okay with interventions and spontaneous? Okay. So this then brings us to actually Jared's question. What is it that makes things spontaneous? And guys, the bottom line is this. Things that are spontaneous don't need a nudge. And guys, if you think about our idea of that metal block and energy exchange, that nudge is that outside intervention is an addition of energy. So if in order for things to happen on their own, if you can't nudge them, the idea then is instead of having to put energy in, energy comes out. So in order for a process to be spontaneous, it has to lose energy to its surroundings. So how does this happen? Well, for example, balls always roll downhill, right? If you've got a ball at the top of a hill, if you've got Mr. Knappenberger on his bike up at Snowbird on Saturday, after I hauled my butt up there, guys, all I've got to do is turn my wheels downhill, and my next stop's going to be in Salt Lake. I don't have to do anything. I'm up there, and I will spontaneously roll downhill, right? And as I do, I'm losing energy. I'm losing potential energy as I roll down into the valley. So the idea here, guys, is that balls and Knappenbergers on bicycles roll downhill without any intervention. I don't need anybody to push me downhill. I'm going to need probably somebody to push me uphill because I haven't rode hard in a couple weeks because I've been grading your tasks. But, guys, it's downhill spontaneously.
So what is gravity? Wouldn't gravity be a form of nudging this?
Here, so the gravity is a force. And again, this is why I don't teach physics, because I hate it. Your question is brilliant. But when we talk about this whole idea of context and system and surroundings, we don't include gravity. And I totally get it, that you're thinking, wait a second, gravity is something that's influencing me to go downhill, right? But the problem is it's kind of like, forgive me, it's like having your cake and eating it too. The idea is that because we attribute the energy that a ball has at the top of the hill, because we attribute the amount of energy that that ball has to gravity, that we can't then say that gravity is also causing this, because we've already accounted for it in the fact that it has energy as a result of gravity, and as it loses that energy, we've already done the gravity thinking relative to the potential energy it has from being up there. So we can't like double dip, if that makes sense. I know it's not a really satisfying answer, but that's the idea. So let's say it this way. Gravity causes the ball to have energy, and then when it releases that energy, yeah, gravity is a component of it, but we don't think of it as being an external intervention. Is that okay? Whew, that was a tough sentence. Yeah?
So a pedal on a bicycle, rusting, would that be considered as spontaneous?
How about nails rusting? Yeah, how about that? Yeah. Because my carbon frame bike doesn't rust. But the answer is, your question is really good, Gavin. So what are other examples of this? Well, and I want to talk about both of them. I was hoping nails rusting was next so I could just jump in where Gavin got us. Hold on a second. Let's do these out of order, because I want to talk about this idea of rusting. I was going to grab this, but that doesn't rust. So guys, imagine that we set a steel frame bike, because aluminum doesn't rust. We can talk about why later. It's already rusted, actually. But why did nails, well, let's say it this way. If you took a nail and set it outside, do you have to do anything to encourage that thing to rust? It rusts all on its own, right? So that would mean that it's spontaneous. We don't have to do anything to make it happen. So if we don't have to do anything to make it happen, what do we know that's got? What is that doing? Nails rusting has to be doing what? Giving off energy, right? And guys, that connection is always true. If it gives off energy, it's spontaneous. If it's spontaneous, it gives off energy. It's one of the few things that you can count on. There are no exceptions. Just a second. There are no exceptions to that. If it gives off energy, it's always spontaneous. If it's spontaneous, it always gives off energy. So when a nail rusts, how does it give off energy? It is slightly exothermic. It's so indetectable, if that's a word, that you'd never be able to like heat up water with it or measure that change in a calorimeter, but nails rusting do give off energy. Second. So guys, with that being true, do any of you have any heartache about this? Yeah, okay. So here's the heartache, right? So we turn on the Bunsen burner tap. I did this once and it was a really bad idea. You can actually light this, don't. But so guys, we understand that methane is a hydrocarbon, but if we were to feed this through a Bunsen burner, we could open up the gas tap and just let it go and it don't burn, right? But now we're saying that hydrocarbons burning is a spontaneous process. So where's the rub? You got to start it. And so guys, remember what we talked about last year about activation energy. So here's the CH4 and the O2. Here's the carbon dioxide and the water. And there's the activation energy hump that this has got to get over. How is it that we add that activation energy? With the striker. But then guys, once we've added this activation energy, the net reaction is exothermic, meaning that it is spontaneous. So the idea is this: when we talk about this idea of outside intervention, it doesn't mean that we don't add, that there could be an activation energy hump to get over. But once we get over that activation energy hump, do we have to sit there with the striker and keep doing it to keep the Bunsen burner lit? No, that's spontaneous. So when we say no outside intervention, that's discounting maybe an initial input of energy that we have to do to get it over the activation energy hump. Is that okay? Yeah.
So like your bike's at the top of the hill, but it's like completely flat.
Yeah.
So if you push someone down the hill, then it's still spontaneous because it's there. That's my question. What is considered outside of invention?
Right. You know, it's funny, Everett. I don't know if I'm comfortable with that. Because if you're talking about this, right, this is how I learned to ski. A buddy took me to the top of the hill and pushed me till it went downhill and then let go. So the idea is if this is the ball here and if you push here, if you were to stop pushing, it could just roll to here, right, which means it stops, which means that wouldn't be spontaneous. So it would be a question of whether you pushed it to the precipice. And at this point, then it would go, right? So I don't know if this analogy maps onto this necessarily, but the thing that we do need to be comfortable, and maybe it does, I'm not saying it doesn't, but the thing we've got to be comfortable with is if we do in fact need to add an initial amount of energy to get it going, that does not discount outside intervention. So Jared, your question then was what is outside intervention? You could think of it this way. It's a little push, it's a little spark, it's a little something that gets it going. But the minute you remove that little push or spark, it goes on its own. So really, when we think about spontaneous, think about goes on its own. So maybe it would be, I'm sitting here on the very edge, and you give that a tap, and then it rolls. Or what about this? What if it's like that, and there's like a parking berm at the top of the hill at Snowbird, and you've got to get me over the parking berm, and then I roll on my own. So I got my front wheel up against a parking barrier, you push me over that, and then I'm gone. That would be more, that's a little corny, but yeah, go ahead.
So with the nails, just like putting that in an environment that where it costs, is that like the outside intervention?
Yeah, no, because then it's system and surroundings, right? Because the reactants have to be present. If there isn't the other reactant, then we can't even talk about the reaction because it ain't there. So if you've got your, and really a nail would rust even if it was sitting here on my table. We put it outside because the water and the heat and everything else encourages it. But a nail's gonna rust anywhere. It's in oxygen. But you at least have to get them together. Is that okay? Go ahead. Well, remember, you can't have one without the other. So while the oxidation is going on of the metal, the oxygen is actually being reduced. It's picking up electrons from the metal. So because you can't have one without the other, they aren't opposites. It's not like it's oxidation in this direction and reduction in the other. It's both in the same direction, so they'd both be spontaneous. Is that okay? I know how you could think of it as one's going in and one's coming out, but they're both going that way. You've got iron, you've got oxygen, they turn into iron oxide, the iron's losing electrons, the oxygen's taking it in to go that way. You guys go ahead.
So does that mean that nuclear fission is helping this reaction?
Nuclear fission? No, because it doesn't happen on its own. Wait, well...
Once it gets going, it doesn't stop.
Oh, I see what you're saying. Yeah, in that case, yes. Because once we start it, it goes like, yes. So, I mean, if you think about like the bomb we dropped on Hiroshima, we all saw the video last year, they add that activation energy from the explosive. And so in that case, yes, nuclear fission would be spontaneous.
That is fusion spontaneous.
I don't...
Once you get it pressured enough, it begins, but is it the pressure constantly there making it non-spontaneous?
I frankly don't know. We don't have to apply this in the context of nuclear processes. We could talk about it individually, but it's not pertinent to what you need to know. So, you guys okay with this idea? So let's bottom line this because this is about to get weird. You ready? So why do balls roll downhill? They lose energy. What kind? Potential. Guys, why do hydrocarbons burn? They lose energy. How? Whoa, how do they lose energy? Heat, right? Why do nails rust? They're also losing energy through the form of heat. Now guys, what about this? What about a quick cold pack? If you aren't familiar with quick cold packs, guys, the way it, well, let me see if I have one. Some of you maybe have never even seen them. I think there's one in here. Yeah, right there. So guys, here's an instant cold pack. I don't know why I never thought to grab one of these before. So if you don't know how this works, you can hear the BBs in there, right? That's actually ammonium nitrate. Typically it is. Yep, ammonium nitrate. Okay, so guys, those BBs that you hear in here are ammonium nitrate. And then inside of there, I don't know, can you even see it against the light? Can you? Kind of. There's a bladder of water inside of here. And so in order to get this to go, it's not cold right now, right? What you do is you squeeze it. And all that does is it bursts the inner bladder, and so the water and the ammonium nitrate come into contact, and what does this thing do? It gets cold, right? So let's talk about it. The ammonium nitrate is interacting with the water. It is actually a chemical process. It's a little more than dissolving. We'll talk about it more later. So the ammonium nitrate is interacting with the water, and as that happens, it feels cold. So is the reaction between the ammonium nitrate and the water endo or exothermic? Endothermic. See guys, heat is going into the bag. Where does that heat come from? Our injured flesh. So heat is transferring in this direction. So this process is endothermic, pulling heat off of whatever we touch this to, and it serves its purpose. Now here's the thing. Once we break that bladder, do we have to do anything to continue to get this reaction to take place? Do you see the problem? Is the reaction inside the quick cold pack endo or exothermic? Endothermic. So is it taking in energy or giving off energy? Taking in energy. Is it spontaneous? Yes. So guys, yeah, that's why it's under exceptions. But guys, you've got to understand this is the important transition that's going to make chapter 19 possible for you. Because now you're having this moment of tension, right? Because we established earlier that spontaneous reactions happen on their own. Things like balls rolling downhill and nails rusting and methane burning. And so we understand that those things happen on their own because they're giving off energy. But now if we separate the two thoughts, spontaneous means happens on its own, right? When I break this, that's that little bit just to get the reaction going. You have to bring them together. When I break this, the ammonium nitrate and the water come together. And does this go on its own? Yeah, I don't have to do anything to keep it cold. I don't have to move it. I don't have to shake it. It just keeps reacting. So is it spontaneous? Yes. But does it give off energy? Yes. Here's your problem. Here's your problem. Guys, your problem is that you have too narrow a definition of energy. When you think energy, all you got in your toolbox right now is heat. Well, in gravity, but we don't deal with gravity in here. But guys, in your toolbox, the only thing you've got in your head is that energy is given off through heat. When methane burns, when nails rust, that's all you got is heat. But now you're seeing heat going in for a spontaneous process, and you're going, wait a minute, this doesn't jive. Something's not right in my world. Guys, the reason that this doesn't jive is because you don't understand enough about energy and the forms that it takes on and the ways that it can be exchanged. So, we have not violated any rules. So let's talk about the quick cold pack, and if you've got this written down in your notes, you may want to supplement this with some thoughts. Is a quick cold pack spontaneous? Yes. I would write down spontaneous. It is spontaneous. But in terms of endo and exothermic, which one is it? It is endothermic. So guys, the question then becomes, how can that be? How can it be, sorry, I need to catch up here. How can it be both endothermic and spontaneous? And guys, the answer is, we need to expand our horizons and talk about another type of energy. So guys, If energy's got to be lost in order for a reaction to be spontaneous, and it does, how do we explain, and that should be this, how do we explain this exception? Oops. Thank you. I pulled out another example because it would be distracting at this point. So guys, that's the question before us. And to answer that question, we will then unpack this riddle. How is it that a quick cold pack is spontaneous and yet endothermic? And guys, the answer is this. Our definition of energy is too narrow. So guys, here's where we're going to get today. We are going to define some terms and we're going to bring them together. And then, given these new terms, we are going to play a little game, kind of like the metal block game. Only instead of a metal block, we're going to talk about a different object. But we're going to talk about energy changes through a similar type of thing. At that point, we're going to call time out. We're going to let time expire. We, on Wednesday, are going to rewrite our tests. And then on Friday, you know what, guys? And I promise I'm not doing this to buy myself more time. We may actually rewrite tests on Friday and finish this conversation on Wednesday, because I fear letting 5 days go by between now and coming back to this. Is that going to be a heartache for anybody if we do that? Has anyone scheduled around it in that way? I hadn't even thought about that. I mean, I don't know if some of you are going, hey, I have a golf something or other. Is that going to mess you up? Okay. It might be better. Actually, that may work out better for you because you can get the information in the screencast. You can't have the experience of working in groups. It's actually to your advantage. Guys, I think we may do that. Anyway. No, because you've got to understand that as much as we're going to spend time on Wednesday rewriting tests, we're going to also spend time talking people down from the edge before they see their scores. Yeah. So, okay, guys, terms. Here we go, terms. Term number 1, reversible process. And guys, you know that most of the time in this class, I encourage you to take notes and not dictations. Write down the spirit of things, although most of you write down every little word anyway, even if they're spelled wrong. But guys, this is a place where you want the words. So what is a reversible process? A reversible process is a process in which it is possible to return a system to its original state with no net change in either the system or the surroundings. What's that? And I'll give you examples of these. Y'all caught up? Not yet? So guys, while you're doing this, let me just tell you, a reversible process is actually, there are millions of examples of this. But to give you something that's concrete enough that you can picture it, kind of like a ball rolling downhill, you're sort of limited in terms of your choices. So guys, let me give you an example of a reversible process. A reversible process would be a cup of ice water at 0 degrees Celsius. So guys, what temperature does water freeze at? 0. What temperature does ice melt at? 0. You get it? So water freezes and ice melts at 0 degrees Celsius. So guys, let's talk about this. Which has more energy, the liquid water or the frozen solid water? They're not the same. Which one has more energy? The liquid water. Because guys, the ice molecules, the molecules that are trapped inside the ice are locked together with these purple sticks, which represent what? Intermolecular forces. Now, in order for this ice to melt, we've got to break these intermolecular forces. And so to break these intermolecular forces, what do we have to do? Add energy, right? So if adding energy causes these to break, then the molecules that are in the liquid form have more energy than the molecules that are in the solid form. Is that okay? Okay, now I'm going to just hold this one out because I need a liquid one. Okay, so now imagine that we've got billions of liquid molecules out here and we've got billions of ice molecules here. Now again, which one has more energy? The liquid molecules. Now, what do? Well, as they're moving around, they're slamming into the glass, they're slamming into each other, and they're also slamming into the ice. Now guys, watch. When one of these liquid molecules with more energy slams into the ice, when they collide, because this one has more energy, what will it do? It will transfer energy to the ice. So this one loses energy. I don't want to pull this apart too badly, but so this one, say it hit here, so this one loses energy. Where does the energy go? Into, good heavens, this one. So this one loses energy, meaning it will slow down and freeze. Where does the energy go? Into this one, which means it will speed up and melt. You get it? So what is the net change to the system? No net change, because every higher energy liquid molecule, when it collides with the water or with the ice, I got to stop doing this while I think. Okay, so guys, when these collisions happen, every higher energy one that collides and loses energy gives energy to one that speeds up and melts. So for everyone that freezes, one melts, and vice versa. So the net change is 0. You get the idea? So guys, what does that mean? It means they're going in both directions simultaneously at the same rate, which we call the condition of equilibrium. So guys, when a system is at this reversible condition, like ice freezing and melting at 0, that is a system that is at equilibrium. So guys, anytime you have a system at equilibrium, it is in a reversible state. Yeah. Absolutely. Yeah, and Caleb, that's why I told you there's millions of examples of this, but they're not great examples to share initially, because if I said, oh, and by the way, the reaction between nitrogen gas and ammonia and nitrogen and hydrogen gas to make ammonia is an example of this, would mean nothing to you because you can't picture that. So this is the best concrete example I can give you. You guys okay with that? Okay, so guys, let's move on then to term number 2, and that would be an irreversible process. Guys, an irreversible process is a process which cannot be undone simply by reversing the events that caused it. Now guys, don't make this mistake. It doesn't mean that it can't go backwards. It can. Irreversible processes can go backwards, but they go backwards through a different pathway, and these different pathways have different heat and work values. I'll show you what that means in just a minute. And guys, I know that this is maybe a little fuzzy right now, I'll show you an example in a minute that will make this more visual, maybe, and that'll help. A new version of Java. I love that that took precedence. Okay. And then, guys, finally this, and you understand that this is where the rubber hits the road. Spontaneous processes. We've already defined this as a process which proceeds on its own without outside assistance or intervention. So maybe you don't need to write that down because you wrote it down previously if you did write it down. But guys, now we're going to make the tie back. You ready? Now that we understand that reversible processes are happening in both directions simultaneously with no net change, and then irreversible processes can't be undone, guys, all spontaneous processes are irreversible. So spontaneous processes always occur in what we call a spontaneous direction, and they are irreversible. This doesn't mean that they can't be undone. They can. You can undo a spontaneous process. It's just that it creates a net change in the system and the surroundings. Yeah. No, they go hand in hand. They're interchangeable. If it's spontaneous, it's irreversible. You can actually use the terms interchangeably, although I wouldn't because they really want you to get to spontaneous. But if it's spontaneous, it's irreversible. If it's irreversible, it's spontaneous. Yep. But understand, spontaneous and irreversible doesn't mean fast, right? Like a nail rusting. That's spontaneous, but it's not quick. So don't confuse it with fast. They like to pick at that on the AP test. Yeah?
So if it's irreversible, it's always spontaneous too?
Correct. Yep, it works in both directions. I got to be careful. If it's irreversible, it's spontaneous. If it's spontaneous, it's irreversible. Those go hand in hand. So guys, here's what we're going to do. We're going to jump out of the notes right here, and let me give you an example that ties irreversible, reversible, actually do them in order, reversible, irreversible, and spontaneous. So I lifted this out of the book. So guys, here we've got a couple eggs. Yeah? They are being supported by a hand. Now guys, when that hand opens, what are the eggs going to do? They're going to fall, right? Once that hand is open, do we have to do anything to those eggs to make them fall? They fall all on their own. We don't have to nudge them. We don't have to coax them. We don't have to convince them. They are just going to fall. So here's our process. Eggs being let go in the air and falling. Is that spontaneous? And so here we go. And oh my gosh, they fall and they smush. I know, right? There we go. Now guys, I know that that's kind of corny, but here's the problem. We've got to come up with examples that you can wrap your heads around. And unfortunately, what appears to be corny may be pushing the limits of your ability to comprehend right now. So let's use this as an important learning tool and get past the fact that this is ridiculously corny. So now guys, what about this? Let's take a look at the opposite process. Smushed eggs laying on a table, jumping back up to the hand. Does that ever happen? Does that ever happen? No, never. So guys, if we've got two competing processes, eggs falling and being smushed, and smushed eggs rising back up to the hand, we understand that falling eggs are spontaneous, rising eggs are not. Does that make sense? So, follow the thinking here, guys, because it's important that you make this, and the last bit of this is going to be sort of surprising. You ready? So first of all, is this reversible? Is dropping eggs and having them smush reversible? It is not. And guys, that's the big point that you've got to wrap your head around. Eggs have a direction that they always go. down, and smush. Eggs have a direction that they never go, back together and up. So tying this to the terms that you understand, this process has a spontaneous direction that it always goes and a non-spontaneous direction that it never goes. Therefore, is it reversible? No. So is it spontaneous? Yes. And guys, that's the big picture. For any process that you have that is spontaneous, it always has a direction that it goes, and the opposite direction it never goes. You get the idea? Now, guys, and this is the tie-in to next time. You ready? Could we make it go in the other direction? Could we reset the clock? Could we take that mess and turn it back into this? The answer is yes. It could be done. We could very, very carefully pick up the yolk and pick up the white. We could take that shell. We could knit the fibers that make up that shell back together, and we could put everything back inside, and we could return it back to the hand in exactly the same pristine condition that it was before it fell. But you know what? That's going to take a lot of work. Literally, a lot of work. And guys, we understand that work and heat are the ways that energy is exchanged. So if we wanted to take this and move it in the other direction, we could do it, but it wouldn't go through the same pathway because it would involve a lot more work to put it together than it initially took when it fell. You get the idea? But now, guys, just a second. Imagine this. If we could account for all the energy that is lost when this falls and shatters, how would that compare to the amount of energy needed to put it all back together and put it back in the hand? It would be exactly the same. It would be exactly the same. And guys, I hope that you find that troubling. Because when this thing drops, it makes a mess. And it's going to take a lot of work to clean up the mess and make it go exactly back to where it was. But guys, the energy lost in this process is exactly the same as the energy gained in this process. So how can that be true? And guys, the answer is this. You see that mess? Guys, we give that mess a name. And what do we call that name? Entropy. And guys, the entropy that is created, and entropy means disorder, and this is where we're going next time. The entropy that is created by that eggshell going all over the tabletop is so great that all of the work that it would take to undo it is just the work that it takes to undo the chaos that's created by that smushed egg. But if we could count up all the energy that is released by that creation of chaos, it would be offset by the amount of work it would take to put it back together. So the energy lost when it falls is equal to the energy needed to put it back together and stick it back in the hand. Crazy, right? So summary, the egg falling and rising, is that reversible? Is it reversible? No, it doesn't go in both directions all on its own. So which direction is the spontaneous direction? Down. Which is the non-spontaneous direction? Does that mean we can't make it go in the other direction? No. So guys, let me give you your homework really quick. Throw your chapter 19 outlines in the basket as you leave. And actually, if you want to, this is posted on our website. Here's our homework. Again, this is posted on our website. You will not be able to do all of these because we didn't get through all the material. Do what you can. Leave your 19 outlines as you go. And guys, I say this in all seriousness. If any of you would like to have the conversation today about, I realize I've just become dead weight and I need to do some serious soul searching about whether I really should be here, I'd love to have that conversation with you. Not because I'm trying to get rid of you, but because I'm hopefully going to help you make better choices. So, guys, turn your 19 outlines in. We'll see you Wednesday.